All right, so today our big focus is going to be on exponential decay. Yesterday we looked at the growth, which was when the function was increasing at a very rapid pace. This time the function is going to be decreasing at a rapid pace, and then it is going to level out. Okay, it's going to get exponentially smaller, but it will never touch zero. So this is going to occur when we're seeing our general form, and this will occur when the b variable is less than 1. Now, someone in period 1 asked me, what if b is 1? Because you notice it could be greater than, it could be less than. What happens if it's equal to? Is it growth, or is it decay, or is it neither? So if you think about it, if b were 1, let's just say 1 to the x power. Let's assume a was 1, b was 1, we just have 1 to the x power. Think about if I were to plug in values. Let's say -2, -1, 0, 1, 2. 1 to the -2 power would become 1 over 1 to the +2 power, which would just be 1. They'd all be 1. So it would not be exponential at all. It would just be a constant linear function, y equals 1. Okay, so that's why you'll notice that in our growth factor and decay factor, there's not an equal bar in either of them. Because if b were 1, it would no longer be exponential. It would be constant or linear. Okay, so our first 4 examples just ask us to, without graphing, determine whether the function represents exponential growth or decay. So again, all you have to do is look at the b value in each of these equations and ask yourself, is it greater than 1 or less than 1? And then write down growth or decay. So the first one, we have 2/3. 2/3 is less than 1. Therefore, this would be exponential decay. The next one would be decay also. 0.12 is less than 1.
Rachel, you left me alone.
How about number 3? Growth. The only way you can really screw this up is if you look at the a value by accident. Okay. You're going to notice that they usually do the opposite, so that if you weren't paying attention. And then the last one is decay. Now I'd like us to add an additional question, bless you. So we'll have 2 number 5s, but that's okay. Y equals 3 to the negative x. Okay, there's one like this in your homework. Now remember, standard form is a times b to the positive x. So most students would look at this and say, oh, it's 3, it's growth. But it's actually wrong. Bless you again. Maybe we should close the windows. If you have a negative exponent, you need to rewrite this, okay, before you can identify if it's growth or decay. So the negative exponent would make this become 1 over 3 to the positive x, right? And then this could also be rewritten as quantity 1/3 to the x power, because 1 to the x is still going to be 1, and that would also give me my 3 to the x. So now you can see that the b variable is less than 1, which would tell me this is decay. Okay, so just be careful that if you see a negative exponent, that you don't classify it right away, because it needs to have a positive exponent before you can classify. All right, we talked about this vocab word yesterday, the asymptote. So again, this is a line that the graph approaches as x or y increases, but it never actually touches that. So we've been seeing a horizontal asymptote at the line y equals 0. It gets really close there, but it never touches. Okay. You also can see vertical asymptotes. We won't see them here in this graph, but some of you may have graphed the rational functions and saw, like, when we got x cannot equal 2, all row numbers, but x cannot equal 2. That was because there was a vertical asymptote at that point. So down here we're asked to graph each decay function and identify the horizontal asymptote. We're going to do this one without a calculator, and then I'll let us use the graphing calculator on the other 2. Now, if you're doing this without a calculator, again, there's going to be at least one of these on the no calculator part. You would want to most likely change your decimals back into fractions, even though most of you prefer decimals. In this instance, the fraction is going to be more useful or user-friendly. So make that 36 times 1/2 to the x power. And then all we have to do is plug in all our numbers and evaluate. So we'll have 36 times 1/2 to the negative third power. Now, when you have a fraction raised to a negative exponent, really the denominator would become the numerator would become the denominator, so they would both switch spots. So really that's the reciprocal, 2 over 1, and then we change that to the positive third power. Then we would evaluate, order of operations, say exponents first, so we get 36 times 2 to the third, which is 8. And then if you were doing this without a calculator, you may need to do multiplication off to the side to figure out what you would get. And we will get 288. Okay, the next one I'll do with you, and then I'll have you guys try the rest of them. 36 times 1/2 to the negative 2. Again, take the reciprocal, which would be 2 over 1. And that exponent changes to a positive 2. Square your 2 to get 4. And multiply those together to get 144. Again, you may need to do multiplication off to the side to help you get that number. See if you guys can complete the rest of the table, and then also plot and sketch your graph. Notice that the axes have already been labeled for us. So we should be getting this as our graph. Again, make sure that you have arrows at both ends. Make sure that you do not have your curve going underneath the x-axis. It does also ask us to identify the horizontal asymptote, which I'll abbreviate HA for horizontal asymptote. That's, for our instances in this lesson, is always going to be y equals 0, because the graph has not been shifted up or down at all, so you don't have to worry about it. But we would see shifts different directions some other times. Okay, let's skip to, let's do just one of these, and let's use the graphing calculator just to speed up the process. Obviously, we've done one without. Let's do one with the graphing calculator. Which one do you want to do? 6 or 7? 7. All right, so go to your y equals. Type in 10 times 0.1. Now, if you were doing this by hand, you would change 0.1 to be what as a fraction? 1/10, okay, because that would help you immensely if you were doing this without the graphing calculator. And we will press second graph to get our table, and then we can just fill in what we see. So I see 10,000, 1,000, 110, 1. Then if you want to do the decimals, you can, or you could also put 1/10, 100th. And then for this graph, you would have to scale your axes to be able to get up to the 10,000. So I might count by thousands, although that's going to get us off the page. So I think there's only 8 here.
Just don't plot that point.
Just plot that point, just estimate it above. It'll just be easier. So let's do 1,000. This will be up to 8,000. So 10,000 would just be like obviously slightly above. If there's just one point that's going to go off your graph and it's like close to the top of the graph, I'm fine with that.
Oh, but if you count by that.
Well, it's going to get so small. You can see how weird these are to graph. Like, you really only can graph sometimes 2 points before they're like so close to 0 you can't even see them, right? Again, horizontal asymptote is happening at y equals 0. Now, the rest of them are our word problems. We're using all the same strategies we used yesterday, except the R value is now going to be a negative. So instead of increasing 20%, it's going to be decreasing 20%. So you'll have to include a negative. The first one is a little bit more complicated than most of them will be in your homework. So we'll go over it. Most of these are going to talk about depreciation, or it'll say half-life, or decreasing 20%. So a car is one thing that depreciates because of the amount of years that you have it and also the number of miles that you would drive on it. So whenever it loses some percent of its value, this is called exponential decay. So here's a graph showing the decay of a car over the first 4 years. Now remember, your decay factor, B is still 1 plus R. R is the annual rate of decrease. Okay, normally they tell us what R is. In this case, we actually have to find R using this formula. Which I don't know that you have to use this formula on your homework, but all you're doing is subtracting the second year minus the first year and dividing by the first year to find the amount of decrease. So they tell us that it started out at 20,000, which you can see, that's like your A, initial. And then at year 1, they actually tell you this is 17,000 so that you're not estimating it because of the graph. But they tell us that over here in the description. So we would take our final value after 1 year, because we're only looking at 1 year at a time, which is 17,000 minus 20,000 over 20,000. It's like the percent change formula, basically. So negative 3,000 over 20,000. And then you will want to type that in your calculator to get it as a decimal, the decimal form of our percent. Now, if you were someone who likes to type like this in the calculator, make sure you group the numerator since it has like more stuff if you didn't want to subtract and do this manually. We should get negative 0.15. That's our R value. That's not our B value. That is the percent decrease. Then we have to find B using the formula that we learned and talked about yesterday. B equals 1 plus R, which is our growth factor. So this would be 1 plus a negative 0.15. So it's depreciating 15% every year. To get that our B value is going to be 0.85. And that makes sense because this is less than 1 and this is a decay problem. Now we're going to write our function, A times B to the X, plugging in the A value that we got. Our starting value is 20,000. The B value we found is 0.85, and then our X. Again, you don't need the parentheses. I just usually put them because of the point. Sometimes looks like a time sign, just to be safe, but you don't necessarily need it. Then they want us to evaluate it for 10 years. And we should say what X is. X was the years since the purchase. It's kind of stated for us in the graph. Usually they don't do that. Then all we're going to do is plug in 10. Obviously needing a calculator to do that. And then just round it to the nearest cent since they didn't tell us what to round to and we're talking about money. So money always would be to your hundredths place. We should get $3,937.49 after 10 years. Okay, so this one was a little bit more involved because you had to find the R value. Most of the other ones you're just going to use the R value that they give us. So the next example is the same scenario. You have a car, depreciating value. Uh-oh. Spoiler alert. One second here. So you want to buy a used car that costs $11,800. So what variable would that be representing in our exponential? The initial, which is our A. Now, it is expected to depreciate 20% per year. You need to attach a negative to the 20% because of the word depreciated. Okay? So this is negative 20%, which whenever we change that to a decimal would be negative 0.2. And the homework is the last page in your packet, guys. Okay. Have a nice break. Thank you. So again, before we can write our equation, we have to find out what our B variable is using our 1 plus R. Now some people also will do this in your head, like 100% minus 20% is 80%. That's what we're going to get, 0.8. Okay, but that's why we're doing this process, is to find out how much is left of it after 1 year, 80%. So then we'll write our exponential model. So 11,800 times 0.8 to the x power. Just make sure you don't put in just the 0.2 or negative 0.2 or 1.2. This is obviously where you can make the mistake in your answer. And then we will evaluate that for 6. So we'll plug in 6 for x and type that and evaluate using our calculator. Again, we'll round to the nearest cent, which we should get $3,093.30. The last two examples are word problems as well, but they're not going to give us a percent increase or decrease. They're going to use a word instead to describe the relationship. So it says the town's population is currently 10,000. So that's our initial population. That's our A variable. The population doubles. So this is your growth factor. If you're doubling something, that's 2 times the amount. So that's actually just telling us straight away that B is 2. The growth factor is 2. So there's no percents involved in this one. There's just a word to describe it. So my equation would be A, just 10,000, times B to the x power. Now it says the population doubles every 38 years. So not every year, but every 38 years. What will the population be 76 years from now? So what number will I plug in for x? 2. Good, 2. So since it's every 38 years, you need to figure out how many sets of 38 years get you to 76, which are 2. And again, that can be found by taking 76 divided by 38 to get you your 2. So we're going to plug in 2 for x. And this one we could do without a calculator. 2 squared is 4. 4 times 10,000 is 40,000. So in 76 years, we'll have 40,000 people in that town. If we wanted to, we could say people. Number 11 is a little science example. Remember I said there's a lot of stuff with like bacteria and cells that have exponential models. So this one, we have, can't even pronounce that. Anyone? Think we can? Actinium? We'll go with that. This one, we want to see how much will be left after 88 years if the half-life is 22 years, and you start with 672 grams. So you start with this amount, that's my A value. When you see a half-life, that's telling us that our B variable is 1/2. Just like doubles was 2, half-life is 1/2. So our general equation would be 672 times 1/2 to the x power. So this is a decay problem. And then we have to figure out what to plug in for x. So we would take 88 divided by 22, which is 4. So we would plug in 4 for x. And we should get 42 grams. See if you can try the closure really quickly. And then our homework assignment is the last page in the packet, 8.1 worksheet 2. The answers are posted on my teacher page. Alright, who can tell me what they got for the number of bacteria? Close. Jaden? 1,200 or 1,200. So you had an extra 0.
Oh, no, actually, I just said that.
You just said it wrong.
Yeah.
Very nice.